One of the things that they're interested in doing, as opposed to what you might have thought about, what I might have thought about the Catholic Church, is that they're very open to looking at ideas that are outside the mainstream, and they're not stuck in, at least in the sciences, they're not stuck in these dogmatic views, for example, of the inviolability of the second law. I don't know what they're like on the religious studies side.
No, I think it's the same way. I mean, they want people to examine their inner lives and to look at the world in toto, humanistically, holistically, and so you can talk about anything you want, pretty much. More so than at a big university where you'll offend somebody and then they'll clamp you.
Right.
So there's more academic freedom here, in my opinion, than you have at a public university.
Well, we certainly couldn't be doing this work.
No, this is a very unusual time and place. We have a big enough university to have support and a small enough university to allow academic freedom. I would have been fired for this at UC.
Yeah.
Huh.
So.
What is thermodynamics?
Thermodynamics is the science of how heat, work, and matter interact, basically. How does heat get converted into work? How does work get converted into heat? What is its effect on matter? Thermodynamics, if you take it apart, you have thermo, which invokes the idea of heat, dynamics, which invokes the idea of mechanical objects of some sort. So if you put them together, thermodynamics indicates that you're looking at how heat and mechanical objects or physical objects interact along with work. So it's the study of work, heat, and regular matter. And the laws that govern them are called the laws of thermodynamics, and there are 4 of them. The 0th law is basically a statement that you can have a thermometer, you can measure temperature or determine what equilibrium is. The 1st law is conservation of energy. The 2nd law is a statement that can be stated in various ways, one of which is that the entropy or disorder in any physical process, or the entropy of the universe, increases for any spontaneous physical process. The 3rd law is a way of finding a fiduciary entropy. So it's a way of, the way it's stated oftentimes is that, for instance, the entropy of a perfect crystal at absolute 0 is 0, which means that a perfectly organized 0 temperature object in principle has 0 entropy. It's perfectly organized. Any deviation, any rising in temperature or any movement away from a crystalline state will increase its disorder. So it's the 0th and 3rd laws, the one dealing with thermometers and the one dealing with absolute values of entropy, are definitional in a sense. They are there to kind of bracket the 2 central laws, which are the 1st and 2nd. The 1st tells you that energy is conserved. The 2nd one says that the entropy of the universe never decreases. So those are the real information content. That's the real information content of the laws of thermodynamics. Clausius has stated it: "De Energie der Welt ist constant, de Entropie strebt an maximum zu," which means the energy of the universe is constant, the entropy of the universe strives toward a maximum. And that pretty much summarizes thermodynamics. Everything else follows from that in principle. But it gets a lot more complicated. I mean, obviously the real world is a lot more complicated and shows more variation than these 4 laws indicate. But nonetheless, the laws of thermodynamics are considered by many to be among the most absolute laws in nature, because they apply virtually to everything. Anything with more than just a few particles, thermodynamics has something to say about it.
Why?
Well, because when particles interact, they need to conserve energy, or the entire system needs to conserve energy, which certainly is within the purview of thermodynamics. And also, since systems tend to explore the range of possibilities that are available to them, they will tend to inhabit that region of possibility space which maximizes their possibilities for existence, which would indicate a striving toward maximum disorder or maximum possibility, which is somewhat the essence of the 2nd law. So whenever you have more than a few particles interacting, like gas molecules, they will tend to, if you throw them in a box, they will tend to go to a maximum entropy state, rather than collecting, let's say, all in one corner where their order would be maximized, let's say. So nature just tends to go toward maximum entropy states. That's an experimental observation. You can make arguments for it based on probability theory, but ultimately it's an experimental fact. All laws of physics ultimately are contingent upon them being observed in nature. You can't prove a physical law. By the very nature, a law is something that is axiomatic, that cannot be proven. It is something that is simply observed about the world. And you can either, whether you agree or disagree with it, the observations of the world are what they are. Theories you might be able to derive from more basic laws, or in regular observations you might be able to explain in terms of your theories. But but the most fundamental things in science, the laws of science, by their very nature cannot be proven. Otherwise they wouldn't be laws. They'd be derivable from something more fundamental. The laws of nature are not written on a wall anywhere. They're not written on the particles of nature, the atoms or the molecules. They are the invisible rules by which everything operates, apparently. And we have to infer what they are from our observations. They're human constructs about what the universe is doing.
Can you give me the definition of the second law one more time?
There is no definition of the second law. There are probably between a half a dozen and 24 definitions, depending on how you want to count them.
Really?
Not all the statements of the second law are compatible with each other. Some are more popular than others. So I can give you maybe the top few if you want to hear those. It shouldn't really be called a law. It should be called a principle in the sense, or a meta law, because it has lots of different definitions and not everyone agrees with what they are. Here's a statement by Truesdell, who was one of the great historians and mathematicians of science. He says, "Every physicist knows exactly what the first and second laws mean, but it is my experience that no two physicists agree on them."
That's terrific.
Yeah.
And that's generally the case. But let me just kind of go through ones that people consider the best and most important. One's called Kelvin-Planck. No device operating in a cycle can produce the sole effect of extraction of a quantity of heat from a heat reservoir and the performance of an equal quantity of work. In other words, you can't take random thermal motion in steam or water or whatever it happens to be and rectify that into some sort of gross mechanical motion, into some coherent motion, without somehow performing work to do that, in which case you somehow have to have created entropy in that process, which compensates for any decrease in entropy in organizing all those molecules in the first place.
Can you give me that in simpler terms?
Sure. The laws of poker and hell, how about that? The zeroth law, there exists poker and hell. First law, you can't win. Second law, you can't break even. Third law, you can't leave the game.
Okay, how about somewhere in the middle about heat and rectification of energy into work?
Okay.
And loss.
Energy in the world is conserved. Energy in the universe is conserved. But when any kind of process you carry out, you can't, there will almost always be an inevitable tax on that energy, which comes in the form of degradation of that energy into a more impoverished form, which you would call heat, something that's less usable. That's a working man's definition of the second law. The second law is a tax on the first law. Okay, one way to look at it. Let's see if I can find, here's a simpler one. There are no perfect refrigerators, perfectly efficient refrigerators. There are no perfectly efficient heat engines. There is no possible process for which the sole effect is that heat flows from a reservoir at a given temperature to a reservoir at a higher temperature. In other words, heat tends to flow from hot to cold, but it will not spontaneously flow from cold to hot. So when you have something like a cup of cold iced tea in a warm room, heat flows from the room into the iced tea and melts the ice. But you're not going to spontaneously have your glass of warm iced tea have it spontaneously freeze and cast its heat into the room. That's not going to happen, ever. So all of this can be, if you look at these various definitions, you can kind of convince yourself that what this amounts to is to say that for any real natural process, the entropy change of the universe will never decrease. It might not increase, but it will never decrease. The entropy of the universe, the disorder, will always tend to increase. And if you're going to impose order on a system, you have to pay for it by creating more disorder somewhere else than the amount of order that you established in the process. That's why I say, when you compare it to poker and hell, when you say you can't win, that's like saying you can't get something for nothing. You can't win, which means you can't get energy out of your system or work out of your system for free. That's the first law. The second law would say you're not even going to keep the work that you had originally. You're going to lose some of it as heat, which you'll not be able to recover and use again. That's why you say you can't break even. means you only can lose. And the final statement having to do with the third law, which says that there's always entropy in any system that you can define, that means you can't leave the game. Regardless of how you want to play the game, thermodynamics is going to apply to you, and you're always going to lose in the end. It's like going to Las Vegas. You play long enough, you're going to lose it all.
Can you talk about any of the things that have been observed, experiments or whatever in history or recently that, at any point in time, that have been used to demonstrate this principle?
The second law?
Yeah.
Okay, I have a nice neat stack of paper here. Okay, I can throw the stack of paper into the air, and it is possible that it will all fly up in the air, flutter about, and land in a perfect stack on the floor.
Right. It's possible.
That's possible. But Tony just laughed. Why? Because he knows it's not going to happen, because he understands intuitively the second law, as does everybody. But it is theoretically possible to do that, and it can happen. But what the second law says is that it's unlikely to happen. Okay? Okay, so anything you do in your life, I mean, just, well, maybe with maybe one or two exceptions, and those don't violate the second law, but almost everything you do in your life increases the entropy of the universe. Just the very act of living increases the entropy of the universe. The only way to stop increasing the entropy of the universe is to shoot yourself and lie in your grave and decompose. When you're all done decomposing and reach equilibrium, you're not increasing the entropy of the universe anymore, and that's the only way to do it. It's a no-win situation. You're always going to lose energy into heat, which is why we keep eating. In order to motivate our coherent mechanical motions of our arms and legs and our minds and everything else, we have to keep feeding ourselves with chemical energy and burning it with oxygen from the air. And by constantly feeding ourselves, we can get work out of the system and out of our systems and do mechanical work. But in the process, we're generating all sorts of entropy. We're only maybe 20% efficient. The rest of it goes into heat, maybe more than that. But we're incredible entropy generators. Life itself is the second law's greatest ally, because by the act of living, we're constantly driving cars, we're building nuclear bombs, we're burning fossil fuels, we're cleaning up our rooms. Everything we do, everything about life generates entropy, far more than the chemicals, the inert chemicals, if we were to be decomposed into inert chemicals, would do themselves. When I was a kid, I used to argue with my mom about this, because it turns out that even when you clean up your room and turn it into what you consider an organized state, you've had to use the vacuum cleaner, you've had to use a broom, and you've had to do a lot of work in order to clean it up. The very act of cleaning up the room creates more entropy, more disorder on a universal level than if you had just let the room in its messy state. So I used to order.
You must have been so hard on me.
So I said, Mom, look, if I don't organize my room, then I'm saving the world from a disorganized heat death. She never bought it, but it's actually true. If you really want to keep the world organized, don't do anything at all.
How do you define it?
Entropy is a measure of disorder. That's the common definition. But actually, nobody really knows what entropy is either.
I just thought it meant some sort of de-escalating into disorder. In other words,
that process is actually
process.
that's a process. But entropy itself has various definitions. The book here that I've written with Vlada has 21 different versions of entropy, and there are probably another 30 which have been discovered as well. Entropy can be defined in fairly reasonable terms only for equilibrium systems. For non-equilibrium systems, which is virtually any system of interest, because we're only interested in how things change and the dynamic nature of the universe, entropy cannot be well defined for non-equilibrium processes. No one knows how to do it.
And what is a non-equilibrium process?
A non-equilibrium process is one that is changing in time, basically. A non-equilibrium process is a process which causes the system to change its macroscopic characteristics like pressure and temperature. It's like a ball rolling down a hill. Once the ball is at the bottom of the hill and stops, that would be considered equilibrium. But any time the ball, say, is rolling down the hill, so to speak, or bouncing or anything, that would be considered a non-equilibrium process. That's a poor description of it. Equilibrium is a state where the macroscopic properties, thermodynamic properties of a system like pressure and temperature are no longer changing. Anytime these things are spontaneously changing or being changed from the outside, then that's considered a non-equilibrium system. It's a process and change. The problem with talking about it this way is that the whole arrow of time is, and the second law are entwined with each other. Why does time go forward? Why did all of these pieces of paper flutter to the ground, and how come they don't pick themselves up and come back into my hand in reverse? Why don't they? The energy is there, but it doesn't happen. There's a particular arrow of time. There's a particular tendency of the universe to move from one level of entropy to a higher level of entropy, and that in a sense defines the direction of time. So it's sometimes difficult to define non-equilibrium without defining time, but as soon as you start talking about time, you're almost implicitly implying the second law. It's confusing.
So how does the second law relate to equilibrium?
The second law would say that systems tend toward an equilibrium state, if given the chance. That is a state toward maximum entropy.
So equilibrium implies a movement towards entropy?
The second law, yes. An isolated system will tend to move toward a maximum equilibrium state. And when it reaches a maximum equilibrium state from which it doesn't change anymore, apparently, that's called equilibrium. So you can consider equilibrium to be the maximum equilibrium state of a system. In terms of the second law, I mean, there's the last section of this book is called the Second Law Mystique, and I call it that because there's can I read a little bit? Do you mind? Okay. Perhaps more has been written about the second law across the breadth of human knowledge and endeavor than about any other physical law. Direct and indirect references to it can be found in all branches of science, engineering, economics, art, literature, psychology, philosophy, and the popular culture. Quite aside from its profound physical, technological, social, philosophical, and humanistic implications, the second law is famous for being famous. It has become the epitome of scientific truth, notorious for its absolute status, virtually unquestioned by the scientific community. Much of its mystique can be traced to the imprimaturs of scientists like Einstein, Planck, Eddington, Fermi, Poincaré, Clausius, and Maxwell. Their reputations are reciprocally burnished by association with this fundamental law. Thus, a cycle of mystique is established. The following are representative quotes from sciences and the humanities dealing with the second law and its absolute status. Outside of theater, rarely does one find such melodrama. Okay, from Eddington. Eddington was considered one of the great scientists of the early 20th century, right up there with Einstein. The law that entropy always increases, the second law of thermodynamics, holds, I think, the supreme position among the laws of nature. If someone points out to you that your pet theory of the universe is in disagreement with Maxwell's equations, then so much the worse for Maxwell's equations. If it is found to be contradicted by observation, well, these experimentalists bungle things sometimes. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. Einstein wrote, so to speak, classical thermodynamics is the only theory of universal content concerning which I am convinced that within the framework of applicability of its basic concepts will never be overthrown. Now when statements like this get popularized, and these are probably the two most famous statements concerning the second law, there grows around the second law this mystique, which if you even question, you are pretty much thrown out or ostracized from science. And so what we're fighting as much as the difficulties of the experiment we're proposing is the second law mystique, which is an invisible, self-imposed censorship that science has put upon itself about what it can speak about.
The dogma.
It's worse than dogma because, well, it is, you're right, it's dogma. But it's a dogma that has associated with it an extreme amount of ridicule, which tends to dissuade people from even entering the subject. Because one word that we have cautiously avoided up to this point is the term perpetual motion machine.
That's not allowed.
There you go. So we tend to avoid the word perpetual motion machine. Instead, you hide behind the word Maxwell demon. Maxwell demon, of course, is legitimized by the great James Clerk Maxwell. But if you use perpetual motion machine, the ridicule that goes behind that can be traced all the way back to Leonardo da Vinci in the 14th century, 15th, 16th century.
If I were to get in an argument with you about the second law,
Yes.
or if somebody gets in an argument with you about the second law, and they just insist that, that the second law is defines such and so, and anything else is you cannot be in violation of that because there's no such thing as violating the second law.
Mm-hmm.
What kind of argument, how would you paraphrase my argument?
I say it's, well, first of all, I'd say it's unscientific, because you can't prove a law. By the very nature, you can't prove it, you can verify it. You can observe it over and over again, but if you believe Popper, for instance, and this is somewhat simplistic, but Popper would say, the only valid laws of nature are always intrinsically falsifiable, which means that if you can't find if you can't at least come up with a, well, how should I put it? To claim that a law cannot be violated really doesn't make sense, because a law is only a law if it has a possibility of being violated. In other words, you have to, a law is an observation about the world. And it is true as long as it keeps being observed in the world. As soon as it stops being observed in the world, or as soon as you find an exception, then you can say that it is no longer a law or needs some sort of modification.
And can you talk to me a little bit about Maxwell and what he observed and what his involvement was?
Well, Maxwell didn't really, Maxwell was a theoretician primarily, but in regard to the Maxwell demon, what Maxwell was trying to do was what he would say, pick a hole in the second law. And the way he was trying to do that was to envision some sort of little creature, which was later, I think, called by Lord Kelvin, was the person who first named it, the Maxwell demon, which was a small creature which could, on an individual atomic basis, sort atoms, either by sort one into one chamber, sort another one into another chamber, such as to create, let's say, an artificial temperature difference between two chambers. By creating a temperature difference, you can create a heat engine by which you can do work. So this little creature essentially takes an equilibrium gas, one with maximum entropy, all mixed up, and sorts it out into two kinds of particles, fast and slow particles, and then uses the difference in their temperature or their energies to do work. This would subvert the second law, because you've taken an original high entropy equilibrium state and turned it into a system whereby you can actually get more work out. And that would be forbidden by the second law. You've taken disorganized state, created more order by sorting the particles, and then using that order to do work.
And lost nothing.
And lost nothing. So, but it relies on the sentience of your Maxwell demon. The demon himself has to be able to see the particles, and there have been arguments saying that he wouldn't be able to do that under equilibrium configurations. He would have to be able to think and be able to sort lots and lots of particles, maybe a mole of particles, 10 to the 23rd, something like that, which would be very difficult computationally. On top of that, he'd have to store the information in order to do, and ultimately have to erase it. And apparently the erasure of the information is the Achilles heel of the Maxwell demon. The process of erasure ultimately creates entropy, which offsets the entropy decrease that he created by sorting the gas. So, at least in my mind, it's fairly well settled, and I think in the scientific community's mind, it is basically settled that the sentient Maxwell demon won't work. On the other hand, there are 24 or more non-sentient Maxwell demons which have come to light in the last 10, 15 years, which apparently have not been refuted by the scientific community and do possibly hold a chance for violating the second law under certain extreme thermodynamic conditions. And that's what my colleagues of mine and I have been working on here at USD, and also what about a half a dozen other research groups around the world have worked on. The one that we're proposing in semiconductors is the only one that I'm aware of that is concrete, experimentally verifiable, and can be done at room temperature, and would have a very clean-cut result. The rest of them are more exotic. Okay, to introduce this particular Maxwell demon, take a piece of common aluminum foil and bite on it with a metal filling, and it's usually found to be pretty unpleasant. What happens is that you have electrons which can be transferred between the different metals, between the aluminum and the silver mercury amalgam in the filling. And as the electrons are transferred between the two metals and kind of even out between them, this charge transfer amounts to a current which can be felt through the nerves beneath the filling and gives you a slight and unpleasant shock. This demonstrates that when you bring two metals together, you get what's called a contact potential, which is the potential difference between two different pieces of metal, two different kinds of metals, as the Fermi levels, as they're called, even out between the two metals, as the water levels of the electrons, so to speak, find a common level. That causes one metal to charge positively, one to charge negatively. and that establishes a potential difference between the metal, a voltage, usually on the order of about a volt or so. Well, the same kind of thing can happen if you have two different kinds of semiconductor. Semiconductors, of course, are ubiquitous in society. They're things largely made out of silicon. They're small, very small devices, and they're doped. That means contaminated with very small impurities, 1 part in a million or so of impurity elements. There are two basic kinds of impurities, ones which render up electrons into the silicon lattice, and ones which create positive holes in the silicon lattice. The ones that liberate extra electrons into the lattice are called N-type semiconductors, and these would be created by doping, let's say, 1 part in a million or so into the silicon of something like phosphorus. On the other hand, if you were to dope it with a different element, something like boron, that would create excess holes in the lattice. And you can create two different kinds of silicon, one which is N-type and one is P-type. And if you were to join them along an interface, the ones with extra free electrons, these extra electrons can diffuse into the positive or the P-type silicon, and the holes from the P side can diffuse into the N side. This cross-charge diffusion creates a charge imbalance across a very small region called the depletion region, where you have positive charges here, negative charges here, and this creates an electric field in the silicon and a potential difference between these two pieces of silicon, which is on the order of about a half to a full volt.
Is this a common occurrence, or is this something with specially doped silicon that you have?
Not at all. This is found in your electronic watches, your computers, anything that has a transistor in it. This is what's called a PN diode or an NP diode. These are very, very common electrical devices. They're the mainstay of semiconductor electronics. This process is well known, understood theoretically, and verified experimentally. There's really no question that this occurs, at least within the scientific community presently. Now, if you were to take this particular piece of silicon and kind of bend it around into a new shape, like this, you would still have the charge diffusion right at this junction here, and you'd have a different potential on this side versus this side. This side would be biased positively, this side negatively, by this charge diffusion. If you then wrap this around and bring it down to to a region where you have a physical separation opening between these two, if you have positive charges here, negative charges here, that establishes an electric field across this region, and there will be a potential drop across this region equivalent to the one here. What this electric field does, well, I shouldn't say does, the electric field stores energy. And the electric field energy I can write down, it's proportional to the square of the electric field intensity or strength. The stored electric field energy here turns this device essentially into a capacitor. This is a capacitor which stores the electrostatic energy in the gap. You haven't paid for this. You have not hooked this up to a battery. You have not. There's no external voltage source associated with this. This has established this energy in this yellow region, the electric field, solely by the existence of this depletion region, which is unavoidable. So you now have a capacitor which in principle will stay charged forever. Now, capacitors, they're used in electronics to drive all sorts of things like the flash cameras which Tony has, or cardiac defibrillators you find in an emergency room or something like that. And what a capacitor does is that it stores electric field energy. Well, if this stores energy, it occurred to us whether we could extract that energy somehow. And one way which we found we could do it, there are several ways, and I'll go over both of them, is to use just a small plug of a dielectric, just as a piece of metal is pulled into a magnetic field. Dielectrics are pulled into electric fields. So you can imagine that if you were to put a small plug of material here that moves frictionlessly within this channel, it can get pulled into the electric field. And if this were also a conductor, it could conduct the positive charges and negative charges together and have them short out, which would kill the electric field, leaving a larger electric field ahead of them, which would continue to pull this plug forward in the field. As it shorted out the field here, it would still see a higher field here, being pulled in this direction. The field back behind it would not have recovered as fast yet. The field ahead would always be larger, and this plug can be pulled all the way through the channel. As it comes to the end of the channel, there's no further electric field here, so it's no longer being accelerated, but meanwhile the electric field behind it has been rebuilding itself. Once it rebuilds itself, it pulls the plug back, and the process can repeat again and again. We have shown, based on calculations of real dielectrics with real frictional coefficients, with real electrical conductivities, that in principle you could build a small plug, something on the order of a fraction of a micron in size, which could be pulled in and out through this channel millions of times per second and never really stop. It doesn't require, you require no power source, because the power is being supplied by the electric field, which itself is being generated by thermal processes somewhere else. So this would be a non-sentient Maxwell demon. It challenges the second law by creating organized motion out of thermal processes, out of heat. There is no other power source driving this. So that's one version of a Maxwell demon. If you were to tie a small magnet to it and have it go in and out of a coil of wire, you would have an electrical generator. So you could, in principle, could generate electrical power from this mechanical motion, in principle.
How are you working on this?
Well, I came up with the idea probably about 3 or 4 years ago, something like that. It took about a year to develop it. Dr. Jeffrey Wright was instrumental in helping carry out numerical simulations, as was Andrew Putnam, one of my former students. They've done a terrific job.
Do you have constraints with regard to the weight of the piston, the
Yes.
mass involved, the drag, and all those kinds of things?
Yes, we've investigated what we consider all the salient parameters of the system, including electrical conductivity, dielectric constants, mass, friction, all of these, and we find that if you build it small enough, something smaller than about a micron in size, you can make a device which in theory should be able to perform as indicated in this video.
Have you built that yet?
No, we have not. We would like to. The technical difficulties put it probably at the state of the art of micro manufacturing, maybe a little bit beyond, but we think within the next 5 or 10 years the state of the art for micro electromechanical and nano electromechanical manufacturing will probably reach the point where this could be manufactured if there was the will to do so.
And, okay, does this put out more than it takes in? I mean, does this
Well, I mean,
violate the
again,
second law?
this is a theoretical study we've done. This is not an experimental study. Based on the theoretical studies, yes, it should be able to put out more. It should be able to take energy, heat from the heat bath, and turn it into mechanical work at a power rate and a power density which is rather large, in the sense that if you calculate the volume of this device, each one of these devices will put out roughly a nanowatt of power, which is a very, very small amount. But these devices are very small themselves, about the size of a blood cell. So if you were to stack them all together into something the size of this table, they could instantaneously put out as much power, in principle, as a nuclear power plant. Yes, way. You work out
the problem would be that you would freeze the entire room.
Well, it would freeze. Well, no. See, the problem is that if it's turning heat into work, I mean, it would put out a power level of about 1 gigawatt per cubic meter, but this thing would cool down to roughly absolute zero in 3 seconds if you run the numbers.
So you're not creating energy from nothing. What you're doing is you're converting thermal energy into mechanical energy, and that thermal energy's got to come from something.
That's right. The room is full of mechanical energy. Let me give you a demonstration. If you take this table here, this table is at roughly about 300 Kelvin, okay, about room temperature, 20 degrees C. The molecules in here are all moving about in this table at roughly the speed of sound, but they're all moving in different and random directions such that all their momenta essentially cancel. If you were to divide up this table perfectly into those molecules which are moving to the left, to the right, forward, backwards, up and down, and simply divide those up, this table would decompose at the speed of sound, all 6 parts going in opposite directions at roughly the speed of sound. That's how much energy is intrinsically present in this table in the form of heat. And that's true of everything else. Your shoes, your legs, you, all the other tables, the wall, the ceiling, the air, all of these have intrinsic energy, but you can't tap them because of the randomization of the molecular motions. They tend to cancel each other out, and it's very, very difficult to rectify them. In fact, to rectify their motions creates more entropy than the reduction in entropy that this rectification would imply. That is what the second law says. You can't achieve this rectification without paying for it, and paying for it dearly. So in subverting the second law, what it in principle would allow you to do is rectify the intrinsic heat in a room like this, and as a result, you can run all the appliances in the room forever without ever plugging anything into the wall, simply recycling the heat energy again and again. And that would be a rather wonderful thing. It would be it could in principle be a solution basically forever to an energy problem. As long as the universe is not frozen, it will have plenty of energy to run itself. It's all present here.
And you could, in theory, have some other thing that generates heat next to it to balance out the...
No, not really. I mean, think about it. If you run the TV camera you're using right now has a battery in it.
Right.
That battery is running it, but most of that energy ends up as heat, which goes into the room. If you had something which could collect that heat and reuse it, it would simply take that heat, turn it back into electrical energy, and run your camera again. So it's not like you've ever lost the energy. It's just being turned into another form, which you could recycle. When we developed this, we recognized that this is the electrostatic equivalent of a magnetic railgun.
Right, exactly.
But it's not magnetism. It's electrostatics here.
Right.
But this is an electrostatic railgun in a sense. No one's ever come up with this, and it only works at a small scale. This will not work on a tabletop size. It will only work when you have very intense fields on very small objects, and for it to be sustained by the intrinsic biasing of this semiconductor requires that it be submicron or in size.
Because of the nature of semiconductors?
Well, because the forces are so small that you only can move small bits of matter, and so you have to build them very small. And to get these these intense electric fields in that gap requires that you build the gaps very, very small.
So there's nothing powering this? There's no power applied to this?
Well, let's be clear about it. It is being powered ultimately by the thermal energy in the device. In other words, the heat in the device is powering it. Because you're not getting energy for free here. The second law is not about that.
But there's no external power applied?
That's correct.
Okay.
That's
There's no voltages being charging the materials?
No, the charging is actually created by a trade-off. What you have here is in the N-type semiconductor you have electrons which want to diffuse out, and you have in the P-type you have holes that want to diffuse out. So when you bring these two together, these electrons and holes naturally diffuse into the other medium, but when that occurs, you get a charge separation, which creates the electric field. So it's a natural diffusive second law process, which gives rise to the second law violation, which is the irony of it all. The second law actually turns on itself here. The violation occurs because you have turned heat energy into macroscopic motion of this piston. That's where the violation comes. You have turned heat into work. That's forbidden by the most fundamental statement of the second law. If you want to define the second law in terms of what you can and cannot do with heat, then what you've done is that you have turned disorganized random thermal motions in your solid into some rectified macroscopic motion of a block of material. You have rectified disorganized motion. That violates the idea that the entropy of the universe must always increase. Here we have shown a way in which the entropy of the universe can decrease. You have taken random thermal motions and turned them into directed, coherent motions of a macroscopic block of material. So that is a statement of the second law which deals with entropy. That would have come about by Clausius in about 1865 when he first discovered entropy. A couple of years ago we hit on an alternate form of this, which actually is superior to it because you can build it more easily. This one requires very fine micro-machining of parts. A simpler version, which we're actually in the process of building prototypes for, is this, where you have the same basic idea. Again, a P-type semiconductor, an N-type semiconductor arranged such that you have a positive and negative potential established between the two regions. Again, the yellow corresponds to an electric field in a gap between an N and P region. We call this the hammer. We call this the anvil. These are very thin slivers of semiconductor which are flexible. Silicon is known to be make very good springs, and these are cantilever springs. So this is a cutaway two-dimensional drawing of it. Imagine you have positive charges here and negative charges here. Under these circumstances, these positive charges would be attracted to the negative charges, and presumably this could pull down the N region, stretching these springs, causing the N region to come down, touch the P region, and short out. Once it shorts out, the electric field has been obliterated, and so there's no longer a pull downward. This material then is released. It gets pulled up by the springs. Meanwhile, the electric field can rebuild in the gap by the same thermal processes that created them originally, and then the attraction would occur again, and the hammer would be pulled down to the anvil, touch, discharge, come back. Now, we have done a number of simulations using realistic physical characteristics of silicon and p-n diodes, and we find that if you can match the time scale over which the electric field rebuilds, which we call the electrical time constant, which should be on the order of tens to hundreds of nanoseconds. If you match that time constant to the mechanical time constant of the spring, in other words, the normal resonant frequency of this cantilever, when you match these two, then you can set up what's called a resonant electromechanical oscillation, kind of like what happens when you push a kid on a swing. You hit them at the right frequency, you can build up the oscillation. Same way, you can use the electric field energy here to build up an oscillation in this hammer anvil and create a self-sustained oscillation. This can be demonstrated using today's technology. It doesn't require anything beyond which has already been developed. And, but again, it has to be built very small. The reasons being, the time constant for rebuilding this electric field are very short. The time constants are on the order of tens to hundreds of nanoseconds, which means that the frequencies associated with the mechanical oscillation have to be on the order of 1 to 10 megahertz, very high frequency, maybe even 100 megahertz. At those frequencies, you have to build the devices very small, otherwise they tear themselves apart by their mechanical accelerations. So they have to be built small to sustain the high accelerations and frequencies, and also to create these large energy densities associated with the electric field. So overall, this thing has to be built probably on the order of about 1 micron in size or smaller to make it work. Nonetheless, this is well within known technology. I mean, modern standard off-the-shelf transistors now are being built down to size scales on the order of about 1/10 of a micron, something like that. So using standard technology, you can build something this size.
And how do you generate electricity from?
Well, again, if you had, let's say, a magnet here on the top of the hammer, and it were moving up and down through some sort of electric coil, it would presumably generate electrical power, like a regular electrical generator at high frequency. But this could have lots of other uses too. But nonetheless, the energy that you could get out of this, or the power you could get out of this, is actually fairly small, on the order of about 10 to the minus 9 watts on that order, 10 to the minus 8 watts, which is very, very small. It's like an ant or a flea crawling up a wall, something very small. But on the other hand, this is very small itself. So although this doesn't put out much power by itself, if you were to couple these to a large number of them, in other words, if you were to have as many of these as would fit in the volume of a desk, about a cubic meter or so, the power output for that desk instantaneously would be on the order of that of a nuclear power plant, about 10 to the 9th watts. Now, of course, that could not go on very long, because if what we're saying is true, then you're converting thermal energy, heat, into mechanical energy. And if you're creating mechanical energy at a rate of 10 to the 9th watts, and that comes from heat, your object's going to cool down very fast. In fact, a block the size of a desk would cool down to absolute zero in a few seconds at that power output rate. The way you would actually use it would be to make large panels of it, very thin, maybe micron-thin panels, spread them out across a wall, and then convert it and make electricity that way. So instead of having a block a meter high, you slice it into 1 million slices a meter, so now you have 1 square kilometer of this material, and then you can use it. It also would absorb energy a lot. It would absorb its ambient heat better. So if you had something like a chalkboard which was paneled over with this stuff, the chalkboard here is about 1.5 meters by about 5 meters. It's about 7.5 square meters. If it's absorbing 100 watts per square meter, you could get about 750 watts of power just from that blackboard sitting there. It would cool down slightly, but it could power everything else in this room continuously forever. You'd be turning the heat in this room into work, and then using our electrical power. That electrical power would run all the computers in the room, and then the heat generated by the computer would go back into the panels, go back into electricity, and then go back into the computers again. You'd be recycling energy. The whole idea of recycling energy is foreign to our way of thinking because of the second law. We naturally assume the energy that we use coming out of the wall or used in an automobile is used once and never used again. But if you were to actually subvert the second law, and again, it has not been broken experimentally yet, but if you could reuse energy again and again forever. It would be completely recyclable energy.
Have you tried filing patents on this? Or?
We published this, well, let me put it this way. In terms of patenting it, we have a company which is which was instituted to protect the intellectual property rights, and we're thinking about what exactly we want to patent right now. But in terms of this was published in Foundations of Physics back in 2002. Any patent rights associated with this have evaporated. This one has not been published per se. It's iffy because this resonant cantilever idea, it's already been tried for ones that are powered with batteries. We're planning on powering it with its own potential.
Yeah.
But we have a few ideas. This one is how to turn this energy into chemical energy. In other words, electrostatic energy into chemical energy. We're working on a paper on it right now. It's unclear where it's going to go. So if you can turn this off the record or just do what you want. Here's the basic.
We won't use it.
No? Okay.
No, but talk about it, but we won't use it.
Okay. Okay. Even if you do, again, it's not going to matter. Again, your NMP region, positive, negative. So you have a positive charges here, negative charges here, and an electric field going down through this material. If you take some sort of neutral atom, bring it in to this, and this can either be inner P material or two different metals like aluminum and your filling. It doesn't really matter what it is. Bring in a neutral atom. The neutral atom can ionize in the surface. This is called surface ionization. I use it all the time in making plasmas. When this desorbs, it gets accelerated by this electric field and will be accelerated across this gap, basically from rest up to the energy, up to the velocity associated with about a 1 volt drop in potential. To put that in perspective, if you take an atom and accelerate it through 1 volt of potential, when it thermalizes, in other words, when it randomizes its motion and comes to an equilibrium temperature, it'll be at a temperature of 12,000 degrees, twice the temperature of the sun. Okay? So you bring in this neutral atom, ionizes, desorbs, comes down here, and when it arrives at the bottom, it has lots of energy indicated by the star, which can stimulate other chemical reactions, basically enough energy to drive a chemical reaction. And then it can just give up the electron again or pick up an electron from the other side and recycle through the system or just leave. But the point is, by falling through this gap, this ion can get enough energy to drive the temperature of your gas up by several thousand degrees in principle, or to stimulate chemical reactions. So we've turned electrostatic energy into chemical energy by this method. But it only happens locally. After all, where did this energy come from originally? It came from heat. So if you let this thing relax again, it's never going to be hotter than what it started at for the whole lattice. But it'll be a local temperature rise of 4,000 degrees. Or I mean, if you spread it out into 3 dimensions, the 12,000 goes to 4,000 by dividing by 3. But it'll go up toward the temperature of the sun, locally. It's really rather remarkable. And all we've used here is the intrinsic bias associated with either metals or semiconductors. Very simple process.
And when did you think of this?
I thought of this summer, actually. I was at a conference in Prague, and there was a physical chemist there. Her name is Tamar Seidemann from Northwestern University. She and I chatted after my talk, and we sat down at lunch and hatched this idea over lunch in a cafe in Prague.
Well, what I wanted to ask you back in the first one with the piston was, what was it like for you to think of this?
Well, I thought of it out of desperation, frankly. I mean, I had been kicked around, professionally, I guess, for about 10 years on these various other second law challenges. The 2 plasma challenges, which I developed in the early 1990s, the chemical ones, which I had done in the mid-1990s, and the gravitational one, which I did in the late 1990s. And so all of these were in exotic thermodynamic regimes, ones which are not easily accessible or testable. When I was in Cincinnati in 1995, one of my friends in plasma physics, a guy named Jeffrey Bowles, we were crossing the street, and he said, plasmas are a lot like solid-state physics. So if you found one in plasmas, there should be one in solid-state physics. There should be an analog. And I didn't know anything about solid-state physics in 1995, but by 2000 I had taught myself enough that I back-engineered the solid-state challenge by thinking about the plasma challenge, which I developed 10 years earlier. So it was really based on a hunch given to me by a friend crossing the street in Cincinnati back in 1995. And he didn't know what he was talking. He just threw out the idea, and I had to chew on it for a while, and I came up with this. And then Jeff Reich got involved after I had come up with it, and we kind of fleshed it out. He was and Andrew Putnam. Those guys were very instrumental in making this thing work. So most of this was serendipitous, but.
I wouldn't mind getting into a little bit about how this wasn't possible 100 years ago, when these laws were formulated because of technology.
Sure. Well, if you look at science over the last 100 years, there is almost no area of science which has not been transformed in one way or another. You can look at classical mechanics where space and time were considered absolutes in the Newtonian sense, and these ideas were shattered starting about 1905 with Einstein's special and general theories of relativity in 1905 and 1916. So the ideas of absolute time and space have been revised. Our ideas about the corpuscular solid nature of matter has dissolved under the development of quantum mechanics, where solid particles now become waves. Our ideas about determinism have been undermined by chaos theory. A lot of our presumptions about the world have been undermined by discoveries in the 20th century. But thermodynamics, which dates back 150 years, was virtually untouched in the sense that people were unwilling to look at the laws of thermodynamics seriously in light of developments in the 20th century and see whether they still applied. There was a mystique around the second law that no one really wanted to attack. Starting roughly around 1990, there was, mid-1990s, there started to be a push toward re-examining the second law in terms of quantum mechanics. And then there were several renegade groups who looked at absolute challenges to it, and we just started picking at it. I don't know why it started. It seems to have been kind of a confluence of a lot of people's work. And there were half a dozen groups around the world that all started working on the same problem, all about this within about 5 years of each other without knowing about each other. It was just rather a coincidence. You had Lindsay Gordon in New Zealand. He was probably the first guy in the modern second law movement. He started about 1980, made some proposals about what biochemical membranes might be able to do in terms of subverting the second law. These articles were largely stillborn. They were more or less ignored by the scientific community. Early 1980s, Jack Deneur from Texas made some proposals about rectifying heat. These were largely ignored. The first stuff, and the new stuff in the 1990s was from San Diego. We proposed about a total over the last 10 years of about 5 different challenges in different areas: plasma physics, chemical physics, gravitational physics, and solid state. There was work by Vlada Čapek from Charles University in Prague. He proposed about 8 or so theoretical challenges which are based on quantum mechanics. And he was looking at membrane pumps and noticed that quantum mechanical rules allow subversion of the second law, basically violating what's called detailed balance in quantum mechanics. A group in the Netherlands and Armenia, Nieuwenhuizen and Alaverdian, showed that quantum mechanical entanglement, which is all the rage now in quantum theory, can give rise to second law challenges as well. They came up with 2 or 3 of those themselves. You also have work by Peter Keefe in superconductivity, where he proposed a very simple mechanism whereby you can use the quantum mechanical superconducting transition to create a small engine, which he calls a magnetocaloric engine. This is closely related to work by Alexei Nikolov, who's looking at with currents driven in superconducting loops, mesoscopic superconducting loops. So there's a whole slew of different challenges out there right now, and there appears to be no general rubric under which they fall. They're all individual challenges. Some of them are related to each other, but there seem to be different groupings, but no overall vision of all of them. No one really knows what connects them all, aside from the fact that they all seem to turn disorder into order spontaneously. In July of 2002, we had what's called the first international conference on quantum limits to the second law, and that was held here at the University of San Diego. We brought together about 120 researchers from 25 countries around the world, and it was the first conference, to my knowledge, in history to discuss the possible violation of the second law or challenges to it. Again, none of these challenges have actually been experimentally verified yet, although there have been corroborative experiments on several of them indicating that the basic processes work. In other words, you can show, for instance, that superconducting transition occurs in a certain way which would be favorable to second law violation. Or my plasma ones, I've conducted high temperature plasma experiments which show a voltage the way you'd expect for second law violation. But it's one thing to show the underlying processes work. It's another thing to actually get useful work out of the system. That's the trick, is to cross all your T's, dot all your I's, and cover all your bases as to where all your heat and work went and balance everything out. It's very difficult to do that in experiments and make an airtight case. But I think there's enough corroborative evidence right now to seriously question the second law.
And your piston idea would be an example of the kind of demonstration that you're
Sure.
looking for.
And this one, I think in particular, the resonant cantilever, if you could build this thing on the size of a blood cell or so and you started oscillating, if it just keeps oscillating forever and doesn't stop, something's fishy going on. I mean, assuming you're not driving it some other way. So you'd have to isolate it from all sound sources, all vibrational sources, all electrical sources, all electromagnetic sources, and then you'd have to do a lot of follow-up tests where you slowly make other ones with less doping and see at what point it fails. You'd build up a case that the second law is viable. The second law is so Loctite and believed by the scientific community that the standards of proof of second law violation are extremely high. And so you couldn't just simply make something that starts vibrating and expect people to believe you. You'd have to do all sorts of different tests and garner and gather enough evidence such that so that any objection anyone raises, you can counter with experimental evidence. When at last you have countered every possible exception and every possible caveat that occurs to anybody, such that they have no further way of arguing against you, then intellectual honesty dictates that they must agree that the second law is viable. But until you exhaust all of these caveats, you're not going to convince the scientific community of the truth of this.
Once you get through all the exceptions and you prove it out, then they just get pissed off and slam the door and you stuck.
Well, they might do that, but on the other hand, if you market this thing and people start buying it and they start creating home power using this, and they're not paying any power bills, then I think people will start paying attention because then the proof's in the pudding. The second law is an experimental observation, so you have to experimentally prove this. You can't simply do as we've done so far and simply write it out on paper and say it should work. That's nice and fine, but maybe nature has a trick up her sleeve which is going to keep you from making this thing work, and you don't know what it is until you try it.
That's also true.
And ultimately, scientific truth is determined by experiment. Theorists, well, let me put it this way, God is an experimentalist. After all, he created the world. If he had been a theorist, he would have written down the equation only and gotten the sign wrong. And so I truly believe that ultimately truth is determined by experiment. Theory can certainly help you out to understand it, but it's not going to determine truth. Experiment determines truth. And so I'm absolutely adamant about this. The second law is inviolable until it is violated.
Right. What were some of the things that they observed back in the steam engine days that caused them to formulate a second law?
Well, the most obvious is that you throw in a bunch of wood into your steam engine or coal with water in it, and you burn all the wood and make steam, and you get a certain amount of mechanical energy out. And when you're all done, everything's a lot hotter, and you can't seem to use that burned up wood again. That's the most obvious observation. You get some work out, but you've created a lot of heat and a lot of entropy ultimately. And you can't get it back. Once it goes off into the atmosphere and the heat dissipates, you can't gather it back again and use it to drive your engine. That's an observation about the world, and it's a very powerful one. It stood all experimental tests for the last 150 years, and before that even, if you want to look back further. So the second law is a very, very powerful and useful law. The question that we're raising is, are there ways of subverting it in subtle ways, which may be useful to humanity and to science ultimately in other ways?
Are there any more obvious ways in which it gets subverted naturally in observable conditions in nature?
Subverted? To my knowledge, there are no. I mean, if there were known subversions of the second law, it would not be a law in the same sense that it is now. It would not be the second law would not be absolute if we actually knew ways of subverting it, or if it was agreed that it was subverted already in nature.
The way the sun works doesn't subvert it.
No, not at all.
Stars work or that.
No, the stars are tremendous entropy generators. Tremendous entropy generators. In fact, it's only by these gradients in entropy that you have life on this planet. I mean, the fact that the sun is a black body radiation source that is at about 5,700 degrees Kelvin, casting heat on this planet, and that we degrade into and use in photosynthesis, solar energy, and so on, and then run our machines and discard that waste heat back out into space. we're always creating entropy in the process, but it actually is a continuous down conversion of the quality of energy as it comes from the core of the sun to the surface, to Earth, back out into space as heat, that keeps this place running. If you didn't have this gradient in entropy, where the entropy is increasing all the way down the chain through all these reactions, we would be essentially at equilibrium now and we'd all be dead. So it's the,
Dead.
well, or hot and dead, doesn't matter. If you go to the core of the sun, you can be hot and dead. But the point is, it's only by the continuous non-equilibrium degradation of high energy sources into lower quality energy sources and heat, or higher entropy, that the world progresses from one state into the other. The universe moves ahead because of its non-equilibrium nature.
So it does make some sense that in subverting the second law, some sort of very clever technological mechanism would need to be employed.
Yeah, it would. I mean, and that's really what it requires. Nature is not going to come up with it itself, I don't think. I'm not aware of any process in which it would, but yeah, you need to engineer the geometry and composition of your devices in such a way that you can create these special conditions whereby heat creates its own downfall, something like this electric field in the gap. Nature's not going to create a device like this spontaneously. And even if it did, it would have to create a perfectly micro-machined dielectric plug to go in and out. That's just not going to happen by itself. The superconducting ones, which are proposed by Keith and by Nikolov, these are superconducting states are not going to occur naturally, except in maybe some very exotic locations in the universe. And even then, it's not going to necessarily result in creation of work. So all of these, virtually all of the ones that I'm aware of have to be man-made, except one possibility. I'm not sure you want to cover this in your talk or not. There have always been speculations that if, in fact, the second law can be violated, why hasn't life resorted to second law violation mechanisms? Okay, that's a legitimate question. I mean, in fact, it's often used to say, well, the second law is absolute because if it weren't absolute, nature in its soaring cleverness and diversity would have already found a way of subverting it. I don't find that convincing for a number of reasons. The first being that it is not proven that all biochemical processes actually conform to the second law. All the ones that we know of do. But the human genome has 32,000 genes or so, I believe, and makes on the order of, 100 million proteins of some enormous number. Only a small number of these biochemical pathways have actually been explored. And so you can't claim with absolute certainty that that's not the case. But if I were going to bet money, I'd say they probably all do follow the second law. On the other hand, I would also argue that the conditions that you find on the Earth's surface, for instance, ones in which you have lots of energy streaming from the sun to the surface, lots of chemical energy available for plants and animals, is not the ideal condition to have what I would call thermosynthetic life. Now, this word was coined just recently, but the idea is this: there are two basic kinds of life that inhabit the Earth: photosynthetic life and chemosynthetic life. Photosynthetic life takes photons, light, and converts it into chemical energy. That's photosynthesis. It's photosynthetic. Chemosynthetic life takes chemicals and uses raw chemicals for the energy of life. That would be something like you eating a beefsteak, something like that. You're not photosynthesizing anything, even though your shirt's green. You're basically taking chemical energy, breathing oxygen, and combining that oxygen with the proteins and the carbohydrates and getting mechanical work out of it. So
chemical processes.
that's right. So you're chemosynthetic life. Because you have two basic branches of life. Well, what if you were to have some sort of life form that could use heat directly and convert it into work? That would be thermosynthetic life. And so there have been a few proposals for this. I think there is a possibility you could find it in certain places. You'd have to look for a place where it's not competing with chemosynthetic or photosynthetic life, which means if you're going to find it, it would have to be in an energy-poor environment, away from the sun and chemical energy sources. The best place to find it would be probably deep in the earth, probably down a few kilometers where it's dark, and somewhere in an energy desert where there's somewhere like granite, where you wouldn't have very many chemicals available to use. I've looked at the possibilities for this, and it turns out that the cell membrane, I don't know if a cell membrane is, surrounds cells. These can be charged, positive and negatively. It's basically like this. you have a natural capacitor which can be built into cells in principle. And I have proposed, at least in this book, possible mechanisms by which you could possibly take the electrostatic potential, the electrostatic energy, or the electric field inside a cell membrane, and convert it into chemical energy. And that, I think, it's quite a long shot, but it's certainly worth proposing. And it turns out that a lot of the chemical machinery necessary for thermosynthetic life, at least as I envision it, when I proposed the idea originally, I started looking into the biochemical literature, and it turns out most of the basic chemical structures which I proposed already exist in cells, which is rather remarkable. So it's almost like all the electrical characteristics are all in place. But the question is, when would these be employed? I don't know. I'm not sure you could find thermosynthetic life easily, but I don't think that it's out of the question. If we proposed ways of violating the second law which are viable, I think nature, which is a lot more clever than I am, would certainly come up with it too eventually.
I may have this all wrong.
Yeah.
Don't systems far from thermodynamic equilibrium violate the second law?
No.
I'm thinking of something that, again, I may have this completely wrong, but didn't Prigogine?
Prigogine, right.
Prigogine, wasn't he involved in this?
Yeah, he was looking at systems far from equilibrium, but his claim was that this movement of systems far from equilibrium into organized structures, like life itself,
right,
can occur only if they're driven. In other words, only if you keep feeding energy in, can you keep these organized structures going.
right.
And so the non-equilibrium aspect of them is there certainly, but they are large entropy generators also. So he would not he would not support necessarily the violation of the second law in the way we did. On the other hand, he wanted to come to the conference but was too sick to come.
Yeah, he's passed on now.
That's right. He sent one of his students instead.
Okay.
Yeah, but he wanted to come to the conference. He was very interested in this because of his interest in thermodynamics and in organized states. But my impression...
He was a Nobelist, wasn't he?
Yes, 1977, I believe.
Yeah.
But my impression of my readings of his work, he would not himself subscribe to violation of the second law.
What motivates you to we've been motivating this for a long time. You said you talked to your dad about this. What motivates you?
What motivated me?
To get into this?
I grew up with the second law, being the son of a physical chemist, and it's always been in the background growing up. It's always intrigued me. It's a deep subject which touches almost every aspect of our lives. I did it more or less as a challenge, I have to say. It was in the early 1990s, Zurek and Bennett and other people had come to the conclusion that the Maxwell demon would be foiled by his own erasure of information. And that made big news at the time, that the Maxwell demon had finally been slain. And I thought, well, that seemed rather obvious what they were doing. I wonder if the second law really can be violated in a different way. And so I started thinking about it. And one thing led to another, and I started coming up with some ideas with chemical challenges and plasma challenges, and it just kind of led from there. I did not wish to be in this field as long as I have. I expected to be in it for just maybe a few years, but in seeing the extreme resistance and hostility of the scientific community, I dug in my heels and said, I'm not going to take this. And so I just continued to work in the area to try to justify the ideas. And it just so happened that at the same time, several other groups were working in the area as well, and they made headway, and we reached a critical mass, at which point we could actually have a conference. And then that starts to legitimize the field. This conference proceedings is actually published by the American Institute of Physics, which is the main conference proceedings publisher in the United States, maybe the world. Just having a conference which is published by AIP adds legitimacy to the question, which it never had before. So I think that was important. I'm proud of that. But I think at this point there are so many questions surrounding the second law that no honest scientist can legitimately dismiss second law challenges out of hand anymore. It's intellectually untenable to do so. And it's now a political struggle to gain enough visibility and enough converts to get it actually examined carefully. Certainly a handful of scientists, maybe a couple dozen of us who are actually in the challenging business, could be squashed by the scientific community or more easily ignored. But I think ultimately people are going to have to come to grips with the second law, particularly if somebody comes up with a real challenge, a real violator experimentally. they're going to say, well, why does it work? They can't simply ignore that. I mean, it's one thing to ignore theory, it's another thing to ignore experiment. So we're just plugging away. That's all I can say right now. We're just biding our time and waiting for things to develop, working as hard as we can, but ultimately it's a political struggle.
I have another question, or more a question of observation, and it pertains to, I mean, I think we're all agreed that there is, the vacuum possesses a huge amount of energy in it.
I don't, yeah, again, that's a theoretical prediction. It has not been measured, so.
Right.
Okay, it's predicted to have high energy content.
Fair enough.
Okay.
Now, hypothetically or theoretically, assuming that prediction is correct,
Yes.
how would the second law, the rigid application of the second law, impinge on any theoretical ability to tap into that energy or transduce that energy?
I'm not really aware that the second law would put a monkey wrench in the utilization of vacuum energy, assuming that it exists.
Yeah.
Because the vacuum energy itself would represent a new, in a sense, untapped form of energy we haven't been able to actually draw out and use. So the second law really doesn't directly speak to that. That would be more in terms of conservation of energy or the definition of energy. So if vacuum energy exists, it would go into the category of a new kind of energy. Like, originally there was only one kind of energy thought that existed, mechanical energy. And then with the discovery that heat constituted molecular random energy, random motion or heat or something, that heat was a form of energy, then you throw heat into the category of energy also. Then just to boot, you throw in chemical energy. Then when you find out that you can convert mass into energy, you have mass energy. Then when you find the vacuum has energy, you call that vacuum energy. You keep adding new kinds of energy into your definitions of energy, all of which apparently can convert one into another.
Right.
But I don't know anybody who can give a perfectly suitable definition of even energy. I mean,
Yeah.
energy is something that you can, in principle, use to make things go. Maybe that's the best way to put it. But they're interconvertible. That seems to be a property of them. But I've never heard anyone give me a suitable definition of energy. So it's funny because you talk about all these absolutes in science. Second law is absolute. Entropy is always increases, and energy is conserved, but no one can even define what they're talking about necessarily. It's a lot naughtier than people think. When a lot of people think scientists think in terms of absolutes, well, scientists are artists. They have a view of the world which is often very personal, and my view of the world is my personal view of the world, which is more or less orthodox. I mean, I agree about most things with most people in the scientific community, but I'm not orthodox when it comes to the second law. Only in as much as I think that there are regimes where it can be violated. For the most part, I would agree with everybody that the world is free of second law violations. The only place that I run into trouble with everyone else, is that I say there might be places where you can subvert it. It's a very small thing, but it turns out to be very important to a lot of people because they would prefer to have absolute certainty on this issue, and I'm not willing to admit that yet.
Can you take another shot at giving me a sixth grade level definition of the second law?
The second law is the tendency of the universe to increase its disorder.
Now that's different than the conservation of energy. So
That's right. Conservation of energy just says what you start with in terms of energy, you end with. That's all conservation of energy says. You can turn your energy from one form into another, from work into heat, from heat into work, to a certain degree. You can have gravitational energy, you can have chemical energy, you can have rest mass energy, you can have vacuum energy, you can have spring energy, you can have all different kinds of energy, and they might be able to interconvert. But whatever you start with, even after they all transmute into each other, what you start with, you end with. That's all the first law says. First law just says you can't destroy it, and you can't create it. You just have what you have. The second law tells you that whatever the energy that you start with tends to degrade, and you can't regrade that energy into from a non-useful form to a useful form very easily. There's so many different ways of stating the second law that no matter how I state the second law, I'm going to miss something. So I can give you 21 different definitions if you want, but it's kind of like to me, it's almost like a pointillism painting. I mean, you can stand back and look at all the definitions and you have a good view of what the second law is. But you try zeroing in on one little definition of the second law and you got a point and you lost the picture. So the way I think about the second law is in terms of all of the definitions, all the statements of the second law, and say this pretty much covers all circumstances. But any one definition is usually going to leave you a little bit deficient in terms of your overall understanding of nature. I think there are the two key definitions of the second law, or two key formulations of the second law. One deals with entropy and one deals with heat and work. These are probably the two basic ways. In terms of entropy, you would say, for any spontaneous process, the entropy of the universe does not decrease. In terms of heat and work, you would say, there is no physical process by which you can turn heat solely back into work. So one's termed in terms of heat and work, the other one's is written in terms of entropy, but they're somewhat equivalent, probably not exactly.
And in electricity, how does that fall into place in terms of electrodynamics?
In terms of the second law?
Yeah.
Well, if you put electricity through a resistor, for instance, the resistor heats up. That electrical energy, work would be I squared R, or V squared over R, whatever. That in the resistor, that electrical energy turns into heat in the resistor, and basically you've turned it all into, you've changed this organized electronic flow into some sort of jiggled motion of molecules in the resistor, and you've turned coherent electronic motion into random thermal vibrations. So you've turned heat into work. Or excuse me, you've turned work into heat. Sorry, my apologies. So any process you can name, any natural process you can name, aside from the second law challenges, I can probably identify where and how the entropy turns up, but it always does. And it's not, and throwing it up all this paper into the air and letting it fall down illustrates that. This is a standard kind of process. No matter what you do, if you throw water up in the air, it's going to splash all over the place. If you just leave water sitting on the table, it's just not going to sit there. It's going to evaporate and fill the room, which is a more disorganized state. If you breathe and your breath comes out, it just doesn't hang there. It spreads out and fills the room. Everything you do tends to increase the possibilities available to it, to increase the disorder. On the flip side of that, everyone talks about disorder being a bad thing. It's a wonderful thing. I mean, disorder in a sense is a greater complexity and richness to the atomic structure or the atomic description of the universe. The universe becomes richer as it becomes more disorganized. It's just a question of how useful is that new richness to us. We call it disorder, and we call it heat, and we call it friction, and we call it wasted energy because we can't use it anymore. But it's still there at a microscopic level, increasing the diversity of what's going on down at the atomic level. I would not want to see second law violators be used on a universal basis because you'd freeze the universe out. You basically take all the heat, turn it into work, but when you're all done, everything's cold, and you're just as dead as if you had died by heat death.
Isn't it in relation to the universe is continually expanding?
Well, the fact the universe is continuously expanding, that in a sense adds more possible microstates to the universe, and in a sense gives the universe more possibilities continuously in which to play, so to speak. So classical heat death, the way it's described in the 19th century, Victorian heat death as they call it, will never really occur, at least not the way they say. But the real source of entropy in the universe turns out to be gravitational sources, things falling, planets forming, stars forming, black holes forming in particular, and then their ultimate evaporation. That's really where the entropy of the universe increases.
Okay. This may not make the movie. Just to revisit something that I mentioned, I think, during lunch break, or maybe this morning. The work that Evans did in Australia.
Yes.
How does that relate to? I mean.
Well, the work by Evans fills out the picture about how entropy changes occur at microscopic size scales, and exhibits the property or the behavior that short-term entropy reductions can occur in the microscopic size scale. But this has really been known for a century or so. In fact, these kinds of things were pointed out by Maxwell 130 years ago. So in terms of actually violating the second law in a real practical sense, the work by Evans doesn't really speak to that point. The work was very good.
Yeah.
There's no question it was good, solid experimental work with, and confirmed theoretical predictions very well.
Yeah.
But in terms of making any kind of practical device or even a theoretically interesting device that would, quote, violate the second law, it didn't really accomplish that, I don't think, because it demonstrated it demonstrates that small systems can, for short periods of time, decrease entropy locally, but in terms of being able to harness that for any kind of real practical use, no, doesn't achieve that. Think of it this way: if I have a box like this, and I let 10 molecules go in this box, they'll bounce around randomly and pretty much be on average spread out all through the box. Would you agree with that?
Right.
Yeah. Every once in a while, all these balls might just all bounce independently, such that they all inhabit one little corner of the box.
Right.
So it would look as if the entropy of this box, of the gas in the box, spontaneously decreased against the second law. That's what it would look like. And you could claim that, in fact, the entropy of these particles all in one corner of the box is less than spread out all over the box, certainly. But you could not have predicted when that was going to occur. There was no necessarily good way of harnessing that, and it was just a statistical fluctuation that caused it. So the statistical fluctuations have been known for a century or more to cause these kinds of spontaneous entropy decreases. Nonetheless, they don't really constitute a useful energy source.
His was for what period of time?
Microseconds probably, or tenths of seconds at most, something like that. I think there is a need to a degree for scientific orthodoxy. It's necessary for science to hold certain standards in terms of truth. If you say anything went, science would be in the same shape as the internet, which is basically just a free
Wild West.
A Wild West. And so you don't want that, but at the same time you would expect some sort of a good degree of inquisitiveness, curiosity, intellectual honesty in the scientific community, which seems to have been lacking in the discussion of the second law. There seems to be a lot of knee-jerk reaction, a lot of unscientific attitudes toward it, which are dismissive rather than inquisitive, or intellectually honest for that matter. The shortest review I ever got on a journal article, which I submitted, and I could paper my walls with rejections from the journals. The shortest one was, this article violates the second law. Do not publish it. And that was it. That was the entire review by the reviewer. That was accepted by the editor as conclusive proof that it had to be wrong, and it was rejected. That is not science. That's intellectual fascism. So on one hand, I can appreciate orthodoxy, but at the same time, scientists should be aware of their own ignorance, which is that no one knows why the second law always works. Nobody knows why. You can't prove the second law. It's an experimentally observed fact for now, but to refuse to admit the possibility that it can be violated is completely unscientific, because it basically throws out the idea of the falsifiability of a law, which is absolutely necessary for the health of any intellectual enterprise. You have to always admit the possibility that you're wrong. If you're unwilling to do that, you really have no possibility of ever really being right. There's always something to be discovered. I don't think there's any end to science or to learning, and anybody who claims that there's an end to science or that they have a general theory of everything, I think should be stripped of their PhD and thrown out of science.
And what was that quote you had earlier? The guy who said we already know everything we need to know. All we need to do is
Fill in the decimal points.
Right.
Yeah.
And that was in what, 1900?
1900. Just before quantum mechanics started.
What was the quote again?
I'd have to look it up, but
Yeah.
it was something like, physics is now officially dead. All that is required now is to fill in the decimal points. Something like that. I think that was genes. I'm not certain of that, but I think it was genes.
What's important about that is not only the fallacy of the statement, but the illustration of the attitude.
Well, the hubris of it, yes, and the arrogance. But you see it now quite a bit in the string theorists, and I shouldn't say just the string theorists, and certain scientists who claim that they're about to have a theory of everything, or a grand unified theory that will explain everything. I find that offensive intellectually, because you can always ask the question, am I missing something? So to make a claim that you have a theory now that answers all possible questions is to cut off further questioning. Once you've done that, you've committed intellectual suicide. And that is the greatest sin that you create. I think that is just about the greatest sin, if not the greatest sin that you can commit as a scientist, is to stop your questioning. I think Max Planck said it best. He said, you never really, how should I put it? Old ideas never really die. It's the proponents of those ideas who die, and it's only then that scientific revolutions take hold.
Right.
So I started this work in my early 30s. I'm 45 now. I expect to live another 50 years, and I'm simply going to outlive the bastards.